Okay, welcome back to Feedback Control Systems. This is Module 6.1. We're going to talk about stability. The objectives of this module are to first start with a definition of stability, then talk about ways that we might be able to determine stability of a system, and then provide an example of those calculations. So first of all, the definition of stability. So in this course, for the most part, we are looking at linear time invariant systems. Also, we call it an LTI system for short. So these systems are going to be stable if the natural response of the system approaches zero as time approaches infinity. So we might ping a system, and we want that, does the natural response decay to zero? Okay, so there's no vibration, etc. As time approaches, do those transients eventually die out? So that's one way to think about it. Oops. Sorry about that. Next, we are going to say that an LTI system is going to be unstable if the natural response approaches infinity as time approaches infinity. So an LTI system, so again, if we ping it and then it starts to grow and the oscillations grow more and more and more, we're going to say that system's going to be unstable. Hopefully, in a real system, you would build in some protection mechanisms to prevent that oscillation from growing to infinity, because usually something's going to break. Hopefully you have, if it's an electrical system, a fuse or some over voltage limiting device, etc. So that's something you would hopefully prevent in an actual real system. We might also say that a system is marginally stable, and that is going to be defined as if the natural response kind of remains constant, or if it oscillates as time approaches infinity. So we'll kind of talk about sort of that as a special case, I will say. And so the highlight of this is shown here in red, that in the definitions of stability, we're really talking about natural response. If we think back to how a system responds, there's really two responses, a natural response, and then if we have a forcing function, whether it's a step input or a force if it's a mechanical system, notice that those, for a stable system, the natural responses will go to zero, and so you're left with any forcing function that would remain on your system. So only the force response remains as the natural response approaches zero. And another way to talk about this is we often refer to LTI systems as having bounded input, bounded output stability, or referred to as BIBO stability. So a system is BIBO stable if every bounded input, so whether it's a step input, an impulse, maybe a ramp, a sine wave, etc. So if the input is bounded in some way, shape, or form, that the output remains bounded as well. Okay, they don't blow up to infinity or something else. So that's going to be our definition of stability. And then a system is unstable from a BIBO sense if you have a bounded input, but the output grows without any bounds. Okay, so it's sort of another way of thinking about our previous definitions. So what are some ways we can look at determining stability? So when we look in the complex plane, the real and an imaginary part here, we're going to look at the poles, the x's, and if we are in that left half plane, where the real axis is negative, poles in the left half plane result in exponential decay or a damped sinusoidal natural responses. So the highlight of that, shown in red, are closed-loop transfer functions that have poles only in the left half plane are going to be stable. Contrary to that, poles that exist in the right half plane will result in some sort of exponential growth or increasing sinusoidal natural responses. Then the definition shown in red, that if you have a closed-loop transfer function with poles in the right half plane and or poles of multiplicity greater than 1 on the imaginary axis, that's going to be unstable. So we're talking right and left half plane, so let's draw that. So real quick, here is our real axis and our imaginary axis. So if I have poles like over here in what I'm going to call the left half plane, if I have poles over here, generally I'm going to be stable. However, if I have poles over here in what I'm going to call the right half plane, So I might have some poles here or some poles here in the right half plane. These are going to be unstable. Okay. Now, the next thing here, the second part of this definition that I show here for instability after this and or is poles of multiplicity greater than 1 on the imaginary axis. So what is that? So if I had, poles here, okay, this is my j omega axis, so if I have poles there, multiplicity greater than 1, then I can basically be unstable as well. So sort of a visual to kind of go along with the words. Now, closed loop transfer functions with only one imaginary axis pole. So one of this, if we could get rid of this one, if I just have one here, then I could be what's called marginally stable. Okay, if I had two, then again, complex conjugates here, but if I have multiplicity here greater than 1, then I could be unstable. So those are our, excuse me, those are our definitions of stability. Now what I would like to do is show some examples of stability. So I have a input here. Notice that the input is 1 over s, which means I have a step input to a system, and I have C of s looking at my output, and I have a system here which is my transfer characteristic forward path plant as shown there. So if I look at that characteristic of G of s, and what I want to do is look at what are the pole mapping in the S-plane as shown here. But I want to draw your attention to the following. These are closed loop poles. So how do I get closed loop poles? I need my closed loop transfer function, which, excuse me, for this course, T of S is what we're going to call. So for the closed loop transfer characteristic. So how did we find that? From a previous module, we said, well, it's the forward path gain. So it's 3 over, in this case, S times S plus 1 times S plus 2 over 1 plus the loop gain, which would basically be this term right here, starting here, 3 over S, S plus 1, S plus 2. And then with regard to the feedback path, it's a unity gain feedback, so I multiply that by 1. So in a previous module, we showed you how to simplify this. Again, I could multiply this by 1, and I would say the fancy version of 1 has to do with this term right here. I would take that term over that term, which is 1. This would cancel, that would come up here, and then rewrite that. So I'm going to leave that to you as an exercise to come up with the closed loop transfer characteristic. We're not showing it here on this sheet, but instead what we're showing you are where the poles are mapped, as shown here. What I want to draw your attention to is when I looked at the open loop system, where are the open loop system? So the open loop system, I'll draw that here. The open loop system, which is, this is my G of S right here, where are these poles? Well, I have a pole here, S equals 0, S of negative 1, and then I have this one at S is negative 2. So here in green, these are the poles of GS, which is that of my plant. However, when I look on this graph, I have closed loop poles. This one here, this one is at minus 2.672. And then these other ones here are off axis, and they look like they are at minus 0.164. So minus 1 here and here. So these poles are at minus 0.164 minus J, and the minus J term looks like it's at 1.047. 1.047, and then this would be minus 0.164 plus J of 1.047. So if I look at that, notice there's a difference between the two. So what we can start to see is when we go from open loop in green to closed loop T of S in blue, something's happening to these poles. So observations for example, we could make is saying, well, between these two poles, these seem like they're kind of going like that, and then they're going off axis, and then this one's kind of migrating that way. So these are some observations. We're going to build into that as we go later into the course, but I just want you to kind of step through and see if you could make those observations. Okay? So one thing to remind ourselves of is we can't just look at the G of S terms here and those poles in terms of determining closed loop stability. That's a very important takeaway I want you to have at this point in the course. So based on these pole locations, I can get the system response that I show here. Excuse me. Notice that there is some damping, some oscillation, but overall it is stable. Why? All of the poles in blue here for the closed loop system are in the left half plane. Okay? Now the next system here, very similar looking system. I have a step response. I'm looking for my output. And notice here, the denominator on the right side is exactly the same green here, same ones that I have. But now the numerator went from 3, okay, to 7. This goes now to 7. And then you could work that closed loop transfer characteristic. Now look at the pole locations. The pole locations for that system, I will put here in, I will say maybe yellow. Notice for that case, this pole goes even farther. Okay, this pole even goes farther, and I'm not going to write the number. You can see it on the plot. Just over -3. What happens to these poles? These poles go off into the real axis, and they're kind of, I'll just draw them here and here. So that's the second T of S that we have on that slide. So if I look, what's kind of happening? Well, this pole kind of went farther this way. And what are we changing? We're changing that gain K. We're changing that gain K that's increasing. So that makes this pole, the GS pole, move to the left, and it makes these poles go, but notice that they kind of go like as an arc here, right? It kind of go as an arc. So at some value of gain K, and we could iterate on K, and eventually we'd get these two on the J omega axis here where it would be marginally stable. But for this gain K7, so we just went from 3 to 7. Look what happened. The open loop poles here, the S plus 1, S plus 2 terms are exactly the same, but now the response is unstable. Okay, so we're going to talk about that as we look at gain and how to make sure we choose a gain to have a good stable system, or to maybe get the response, the transient response that we want. Okay, and so I want to bring that home with this last example down here. A little bit more complicated, R sub S, C sub S, and look at this characteristic. Okay, so that is our G of S term right there. And the forward transfer function looks stable. Again, if I look at those poles, I have S of 0, -4, -6, -8, -10, and then I have a 0 at -2. Everything from GS is in that left half plane. Looks stable, right? Well, just like we saw here, for G of S terms, everything was in the left half plane, but depending on the value of gain we have, that might make those push into the right half plane. So you have to be careful and look at that closed loop characteristic. So I'll leave it as an exercise to use this formulation, as we've done for previous exercises, to come up with this, which will be the closed loop gain T of S. So what we see here circled would be our T of S, our closed loop transfer function. Now, if I look at that, I have a fifth order polynomial in denominator. I'm going to use some math routine to find the roots of that, set that equal to 0 and find the roots. I have 5. And if I look at them, I have a negative, a negative, a negative, a negative, and a negative. All of these are negative. They're all in the left half plane, so that's stable. So I have 5 poles in the left half plane. That system is going to be stable. So let me clear some ink here. And then we can make some observations as shown down below. So the first observation I can make is the following. If the signs in the denominator are not the same, then the system is unstable. So for example, if I have some plus and some minus, I can look at that and say, I can just look at that and say it's not stable. I don't have to calculate the roots, okay? And there's some mathematical routines you can do to kind of prove that beyond the scope of this class. The second observation I can make is if powers of s, in this example I have s to the fifth, s to the fourth, s to the third, etc. If powers of s are missing, the system is either unstable or at best marginally stable. So for example, if in this equation right here, let's say I just didn't have this S3 term. I had S5, S4, S2, and the S to the 1 term. Because that's missing, I can't say it's stable. It's either going to be unstable or at best marginally stable because of some roots on the j omega axis. Okay? However, the third case, if all of the coefficients of S are positive and not missing, so that represents the case we have here. We have S5, S4, S3, S2, S1, and S to the 0. They all have the same sign. In this case, they're all positive here. Then we basically say stability requires solving for poles. So we had to solve for poles here. Okay? So that's very important as we go through this. Most of the time we're going to use some math routines to go through this and solve that. Okay? So that will conclude this module. If you have any questions on any of this material, please don't hesitate to reach out. Thank you.